Welcome to the next talk. We will talk about DCRs, and that downtime is probably not an option for anybody in this room. But the actual title of the next 30 minutes is more like this, so like having fun with DCRs and Big Bang Theory. So hopefully you all see in the series, otherwise it's probably funny anyways. But yeah, let's get started. My name is Johannes. I'm working for the company behind DCRs, it's Mesosphere. And you can find me on the internet, so you can find me on Twitter, or we have a community Slack channel, so it's chat.dcrs.io. So if you have further questions and can't find me on the conference, just drop me a line everywhere, somewhere, and I will get to you later. Okay, so probably you had this feeling the first time you deployed your microservice architecture to containers and really happy and nervous. But sooner or later you get somewhere that you realize that distributed systems are hard anyways, and it doesn't matter if you go to containers or not. So, but let's get one step back. So probably while doing software development, developing a production system, you pass some ways during the way. So the first way is always works on my machine. So you downloaded some stuff, all your dependencies, your runtimes, your databases run on your local machine. And the second step is mostly nowadays run everything in containers. So it's Container Day. You probably all know about the advantages of running software in containers, packaging all your dependencies in this container, make it easily shippable, easily shareable. And so this is great. So we didn't have that in the past century, so and the past decades. So having tools like Docker Registry is huge to like share your applications easily with all your coworkers, with your staging system and production afterwards. But just because you run something in containers doesn't mean that you're production ready. So can you easily put your containers to production? Probably not. Just because you put your application into a container doesn't change anything about your application and the monitoring and all the tools around that. So let's have a look at the current state. You probably currently have something like this, if you're not running Kubernetes or DCS, something like this. You have somewhat infrastructure. Hopefully, you're able to provisioning automatically new machines. And on top of this infrastructure, you have some machines, either virtually or bare metal or whatever. And on top, you have operation system, container runtime, and then your orchestration, and then you're running your services and applications on top. And this is really great. So you're really able to ship and run your applications really fast and do upgrades really fast because you only need to swap the containers on top and not the whole stack underneath. But what we saw in the past and what our reference customer, Twitter, we call it Twitter for the next couple of minutes, they did called spreadsheet scheduling in the past. So it was really 2009, the ages around this. And what they did, they had a huge spreadsheet calling, I need to run service A 1,000 times. And then they sat together each Friday and counting how many applications running these, how many instances these applications running. And if there's 950 applications running, they knew that they need to find space to run these 50 missing images, containers. So we need something that is automatically detecting that something is stopped and restarted somewhere else again. And this is missing. So when we need to talk about production, we need to talk about scheduling. So where to place my tasks, find a slot somewhere on some ship, on some node to start my container. And if it fails, find another slot to restart it. How to handle the scaling, how to handle upgrades and downgrades. So we need to talk about this kind of stuff. And when we're talking about production, we need to talk about resource management, like limiting containers in their need to consume resources. So in this case, it's really bad. So this container consumes all the resources of the node. It's probably bad. So we need to limit CPU, memory, and disk usage as well as IP port consumes. So it's probably also bad if you have a task consuming all the ports on your nodes, but letting all the other resources free. So you need to balance this. And the last part we need to talk about is service management. So we need to talk about that all your containers in your infrastructure are going the same direction, having groups, dependencies, doing service discovery, health checking, readiness checking, and so on and so on. So when we're talking about container scheduling, resource management, and service management, we're actually talking about container orchestration. And as much as I like ships, we don't talk about ships right now, we talk about this. We talk about where to place my task, how to do scaling, upgrades, and even worse, downgrades. So this kind of tricky, even if you're handling data services, you're doing downgrades, it's kind of tricky. On the resource management side, you want to limit your containers to consume memory, CPU, maybe GPU. So GPU is highly asked these days, as well as ports and IP. So you need to limit these kind of things to have a healthy running production system. And on the service management side, you need to talk about service discovery, load balancing, grouping, namespacing, and so on and so on. So a bunch of stuff to talk about when going to production. And actually, your architecture looks something like this. You have your machine infrastructure, machine operating system, container runtime, on top all this stuff I just told you, and then your applications are coming. So you have a big stack to maintain. But in the meantime, MapReduce is crunching data. So our containers are not alone in your world. So you have your applications running your microservices, but somewhere in your cluster there's data, actually data, like big data or streaming or machine learning, something like this. So you need to share all these kind of things. So modern applications, or what we call the SMAC stack, like the modern kind of stack, looks something like this. So you have a bunch of clients and devices and sensors. Imagine like mobile payment or ATMs sending events to your application. And the first thing is you need to ingest these events, like put it into a queue and then maybe analyze and store it to Cassandra. And afterward, do your data-driven applications and visualize your data. So in this whole big world of not only having stateless application, also having traditional databases, big data like Cassandra, or NoSQL, or streaming, and stuff like this, you need to be resourceful with your cluster. And in the best case, you can share the resources between your microservice architecture and your data-driven applications. And this is the point where we as Mesosphere are talking about the modern data center. But again, I want to go one step back, and I want to talk about this. So I'm originated in the Java enterprise world, and what I saw in the past really often was static partitioning of clusters. So you have your big cluster, let's say, for example, 30 nodes, and you decide up front where to start which kind of application. So you decide to pin 5 nodes for Hadoop, 5 for your database, 10 for your Java services, a couple for Spark, and a couple for your Memcache or whatever. But this has a bunch of disadvantages. So when we have a load peak, so you need to optimize all these parts against load peaks. But let's imagine our service part have a load peak, so like really under heavy pressure, and 20% of the nodes failing. It's quite bad, because probably Hadoop is idling in the meantime. So you could easily swap these servers to the other part of the cluster, and it's up and healthy again, but you can't because you static partition your cluster. And the other disadvantage is something like this. So it's a big waste of resource. Applications typically have different load peaks to different times of the day. So Java servers probably have a noise over the day. Spark is probably doing MapReduce over the day and Hadoop over the nights. So you could easily crunch this together and not waste this amount of resources when you do something like this. You have one cluster sharing between your Java services, Spark, and Hadoop. So you need less servers and be more tolerant to dynamically shift the resources between your applications. So another way around, you probably want to have something like this over there. You want to have one cluster and you don't care where to run stuff. You want to be able to run Java, Ruby, Python, Cassandra, Spark, Kafka. It doesn't matter where it runs as long as it runs. So you want to be able to dynamically shift the applications between your nodes. And this is the point where Apache Mesos enters the game. So Apache Mesos was originally invented 2009 at UC Berkeley and was a class project. And these 3 students wanted to write a paper about fine-grained resource sharing within a cluster. So they wanted to share CPU, memory, and disk between different applications. So they wanted to share between different Hadoop installations in the first beginning. And by accident, they gave a tech talk at Twitter. And this was a time where Twitter had these crazy scaling problems. You remember the Twitter fail whale? So the sad whale serving no requests currently servable. So Twitter was not able to cover the new user counts. So what you needed to serve the new users. And this was quite matching this idea of sharing nodes between services, microservices, and data applications was really, really good for them. And they pushed it really forward to get a source code draft in the same year, and short afterwards it enters Apache Incubator, then Apache top level. And then we as Mesosphere started to work and developed something on top. And we open sourced this last April. And we would want to talk about DCS in a couple of seconds. But let's stick to Mesos for a while. So Mesos is running in big installations. So Twitter runs Mesos in production to serve twitter.com. And it's about 29,000 node cluster. I don't know the exact number. They updated it last year, someone. Airbnb runs Twitter. Netflix running their streaming part on Twitter, and Apple runs Apple Siri on top of Mesos. And it's probably the same size like Twitter. And this is quite interesting to see why this kind of dynamic resource sharing is interesting, because Apple Siri is for each language a different installation. And with Mesos, you're able to scale up your application based if your user base is awake or not. And you'll be able to scale down and give the resources back to the cluster if your user base is don't awake. So this is a quite good example for this. And this is how Mesos works. So Mesos is separated between agents and masters. And Mesos agents are the nodes where container are running, or your Cassandra node is running, your Spark node is running. And your Mesos agent is talking to a Mesos master. A Mesos master is all about management. So there are no computation, just for the management. And to Mesos master, on the other side, you could register a scheduler. In this example, you could register Marathon, which is our kind of container orchestration, and Myriad. Myriad is a bridge for running Hadoop on top of Mesos. But you could also register a scheduler for Spark, or for Cassandra, or for Kafka, or for ArangoDB, or for something like this. And let's make an example. So this agent has 4 CPUs and 10 gig of memory free, and say, hey, I want to offer these resources to the cluster. Then the agent will report this to the master, and the master will pick one of the registered scheduler by a fairly distribution, and offer these resources to the scheduler. And this example goes to Marathon and asks, hey, Marathon, do you want to start some containers on these 4 CPUs and 10 gigabyte of memory? And then Marathon can decide if Marathon want to launch 1 container, 2, or to decline the offer and say, hey, no, on this node, I don't like this node. I want to start it on this. I'm waiting for offers from this node. So, and then Marathon can say, oh, I want to do this and that. And the separation of resource negotiation, so resource sharing on the Mesos level, and the ability to plug different schedulers on top is made on purpose. Because this enables a huge variety of different schedulers to run on Mesos. So you can run stateless containers, what we do with Marathon, or Apache Aurora, which is also a container orchestrator for Mesos. And you can run on the same cluster a Cassandra scheduler, or Spark scheduler, or whatever you like to. And the reason is that scheduling stateless applications is way different from scheduling data-driven applications, big data-driven applications. So when a stateless task is failing, you probably don't care if it's restarted here or here. But if a Cassandra node is failing here, you probably want to be restarted on the same data again to prevent the full data replication of gigabytes or terabytes of data. But the great news is you, as users, you're talking to the scheduler. So if you're the user and want to start a container, you're talking JSON to Marathon, configuring how your container will look like and what images to use, what ports to expose, something like this. And under the hood, the scheduler will talk to Mesos and do everything needed to serve your needs. Okay. So when we are now at the point that it doesn't actually matter where to start your containers, it could be anywhere, we definitely need to talk about data. So data in containers is a first-class citizen for Mesos and DCOS, because we all care about data, right? So we want to keep our data in our database, our customer data. We want to keep it safe and persistent. And basically, there are three kinds of applications nowadays. So we have stateless applications, like in Node.js, Nginx, or Tomcat application. And you probably don't care about the data produced by these kind of applications. Maybe except logs, but let's talk later about logs. So you get a default sandbox routed to your container. And then you have two kind of databases. So you have on the one side, you have a scale-up database, like traditional MySQL database. And this kind of database is scaling by adding more resources, by adding more CPU, by adding more memory. But they are not good in fault tolerance when the node fails. So when you would want to have really the highest availability for these kind of applications, you probably won't get around distributed file system and external storage. Sure, you can use backups, but you probably spin up fast replacement when using external storage. And on the other side, you have scale-out databases. And this is really, really interesting. So these are kind of applications written for distributed systems, like Cassandra, MongoDB, Elasticsearch. And they're scaling by adding more nodes to the cluster. And for this kind of applications, we offer a local persistent storage. This is a space on the disk reserved for your application. And when your application goes down, either planned for maintenance or unplanned because of a crash, you're able to restart the replacement on exactly the same data again. So you can do an upgrade, start on the exact same data again, and prevent full cluster replication. This is quite good. Or your container can crash because something happened, and you're able to restart on the same data again and don't need to do replication. And the best thing is, this is local data. So you don't have expensive external writes, so you have the full performance of your local disk. Okay, and that's how we handle data. Great. So now we have all bits together to talk about DCOS. So DCOS is a platform to run microservices in containers together on the same cluster as your big data, as your SQL data, as your NoSQL data, as your stream processing, as your machine learning, and your time series database. On top, and this all operates on top of Apache Mesos. So everything starts on Apache Mesos. On top, you get a bunch of common concepts for security, CLI, UI, networking, and so on and so on. And the great thing is, you can abstract what medium you're running on. So it doesn't matter if you're running on this Mac, or on Amazon, or on Google, or in Azure, or on-premise at home. So you're running on DCOS, and DCOS abstracts all the infrastructure below. And the great thing is, everything I show you today, or told you yet, is open source. So you can go to dcos.io or github.com/dcos, and have a look at all the stuff I told you. So if you go to DCOS.io, you get a bunch of docs, tutorials, and setup instructions. And yeah, it's an umbrella for 30 open source projects. And on top, you get a bunch of service discovery, load balancing, and packaging. Good. But who wants a quick demo? Yes. Yay! Thank you. So this is DCOS. So this is what you see when you successfully logged into DCOS. And what you see is an aggregated view of your cluster. This is probably what you want to see when you get a PagerDuty call in the middle of the night. So you see that you use 12 of your roughly 30 shares of CPU, that you use a gigabyte of memory, and a bit of your disk. And you see that all your tasks are running healthy currently, and you're running 10 tasks, so I've installed something up front. And the fact that you're dealing with a cluster of 7 nodes is just a detail, and you really only care about this number if something if some of the other numbers are wrong. So let's have a look at this navigation. So we do have our service section, and there we see everything what is under Marathon, what is container orchestration, and you see that I installed Cassandra, Kafka, and some other stuff yet. Let's quickly jump over the others and then come back later. You do have the same thing for jobs, so you can run scheduled containers, so like every night at 3 a.m. And you have the universe. And the universe is kind of an app store just for clusters. And you can install the Cassandra cluster just by adding do 2 clicks. And I did this up front because it takes like 10 minutes, something like this. So it's really easy, and we have a bunch of stuff in the universe. So you can use Cassandra, Elasticsearch. Actually, you can run Marathon on top of Marathon if you want to. Or Spark, ArangoDB, and Datadog, Sysdig. We do have a Prometheus package, so everything you heard from the previous talk, you could also apply for DCOS as well. Okay, but I prepared an application for you. I prepared Twitter simulation for you. And this application is a Rails application. And I will start this application via the CLI. So I do DCOS Marathon app at Twitter.json. And what I'm doing here is I'm using this JSON file through the Marathon REST API to start this deployment. And inside this Twitter.json is just defined. The app is called Twitter, do some kind of exports, then start the RAID server, have some resource limitations, start 3 instances using Docker with a host port. And this is a random host port. And I installed up front, yep, I saw you, Marathon LB, which is a dynamic load balancer for Marathon. And these load balancer automatically configures based on the running applications in Marathon. So if I'm doing a magic label in this app configuration, these load balancer will automatically configure and route all the traffic to this kind of application. Good. When we now go back to our UI, I see that the Twitter app is currently deploying, so we have 2 greens and 1 unknown. So I configured health checks. So a health check is done every 10 seconds, and if the app is not passing the health checks, DCOS will take care to replace it somewhere else. And for sure, you can get the details of your task, go to the logs, and see everything. So and see the logs. So obviously, this task is not logging so much, and now we can actually tweet, so we can do Unterstein and hello. So great. So we see our first tweet, and all this is piped through this Twitter application, then going to Kafka, storing to Cassandra. And if I had more time, I would use Zeppelin. Zeppelin is a web UI to paste Scala code into, and then it gets automatically compiled, and you can do Spark, so in-memory MapReduce against all your data there. So this is quite a funny. So, but let's go back to our slides. So I got the cross. I need to hurry up a little bit. I only have a couple of minutes left. So congratulations, our app is running in production. Yes, I see you, but I still have 5 minutes on the clock. But wait, so let's roughly jump through all the stuff you need to do on the next day after your party. So you need to do monitoring. So what we saw in Prometheus, you really need to take care about your metrics and do alerting. Connect it to PagerDuty to get a call when something is wrong. Everything is built in. So in the universe, in our app store, you can install Prometheus, you can install Sysdig, Dynatrace, Datadog, all these kind of applications, which helps you do monitoring. But also you could do advanced centralized logging, like go to Elasticsearch. You can install Elasticsearch cluster through the universe If you want to do pods, like co-location of containers, you can add a side container to have a log stash and go for your log files. And on maintenance level, you can easily upgrade a DCS cluster. So when you're having a high availability setup, just upgrade the non-leading nodes and then upgrade the leading nodes. You can do on the agent side, where you run your containers, you can upgrade DCRs without stopping any of your containers. That's no problem. You should take care of proper backup and disaster recovery and advanced network policies, so what you probably also would do for your non-containerized world. But when it comes to debugging and finding a bug in a distributed system, it's kind of hard. So we offer a set of tools to help you debug your application. So like debug your services, why your container is not starting correctly, not behaving correctly. So you saw the CLI, right? You can do DCS task login and log into your particular container running somewhere in your cluster. And the great thing is you don't need an SSH key for this. You probably don't want to distribute your production SSH keys to all your developers. With the CLI, you have a tool to log in a particular container based on your roll and write concept of the logged in user. It's kind of nice. And you could do the same for system, for your DCRs as well, and you can also debug deployment. So why is my deployment never ending and why something is stuck? So this is all included. So I think for node failures, we don't have that amount of time, but I want to show you, or at least you need to trust me, you can kill this one. Mesos will take care to replace all the containers. You kill the master, the next one will be the next leading master, and you can also stop a scheduler, or a scheduler can fail, and DCS will restart the scheduler for you. Okay, thank you very much, CBS and the Big Bang Theory crew, for providing such a great series, and without this would not be possible. But I have one more, so no talk without cats, right? So thank you very much.